Hello everyone, in this control theory and control engineering tutorial, we explain how to design and simulate in Simulink an algorithm for active feedback control of quarter car suspension system. A simple quarter car system is illustrated over here. As its name implies, this system represents 1/4 of a car, that is, one wheel, its suspension system, and 1/4 of the mass of the complete car. The suspension system consists of the spring with the spring constant equal to C and of a damper with the damping constant equal to B. We assume that the mass of the wheel is much smaller than the mass m and it can be neglected. In this figure, x represents the displacement of the mass m from its equilibrium position. On the other hand, z represents the displacement of the center of the wheel with respect to some neutral horizontal plane. As the wheel travels, the center of the wheel will describe this trajectory. And this trajectory will actually be described mathematically as z is function of time. Then, another important thing should be observed over here. Due to the road irregularities, this function is quite random. Over here, you can see one realization of z as a function of time. This is a stochastic process in time actually. In the control engineering terminology, z represents the input disturbance to our system. If we applied this input disturbance to our system, due to the fact that we don't have control, that is, we don't have a feedback control in this system, x will actually follow this input disturbance. If you, for example, sit in the car, and if you, for example, hit a bump, and if the car reacts like this, that is, if this mass suddenly goes up and down, you will feel very uncomfortable. And we want to correct for that. To summarize, over here you can see an open loop system. Open loop is actually from the input disturbance to the displacement x. And the goal of the control algorithm is to attenuate the movement of x. That is, despite the action of the disturbance z, the control algorithm should smoothen out the behavior of x over time. And this is represented over here. Over here, again, we have z as a random function that's quite stochastic. We can see big peaks and big valleys, and the feedback control should be designed such that x is very smooth. That is, the feedback control algorithm should cancel the effect of this disturbance on the position x. Here is a sketch of a feedback control algorithm. Over here, we assume that we have a sensor measuring the displacement x. On the other hand, the user sets the desired position of x. This is represented by this set point. Then, the error E is calculated. The error E is simply a difference between xd minus x, and this block over here actually computes the error E. Then, the error E goes as an input to our PID controller, and on the basis of the current error E and on the past values of the error E, the control algorithm will compute the control input U that's sent to the actuator, and the actuator actually computes, or better to say, amplifies the control input signal and generates mechanical force F, whose purpose is to stabilize the motion of this mass m, despite the action of the disturbance z. Here it should be noted that this is a very basic control structure. This control structure can be significantly improved by, for example, introducing over here a disturbance observer. This idea will be explored in our future tutorials. By the end of this video tutorial, you will learn how to create the Simulink block diagram. This Simulink block diagram models the system dynamics, that is, the dynamics of the suspension system. Then it models the disturbance. Here's the model of the disturbance. Then it models the PID controller. And it connects all these blocks in a functional block diagram that enables us to visualize and inspect the performance of the feedback control algorithm. Let's simulate this system. And let's analyze the simulation results. In this simulation, we assume that the set point represented by this yellow line is equal to 1. Here the units are arbitrary. Then, this red line represents the disturbance Z. This is the profile of our road over time. Then, this blue line represents the position X that's stabilized by using the feedback control algorithm. We can observe that after the initial transient response that lasts for approximately 1 second, the position of the mass X oscillates with relatively small amplitude around the desired or around the set point. On the other hand, we can see that the disturbance amplitude is much larger. This means that our feedback control algorithm is doing a relatively good job. First of all, it's able to decrease the amplitude of oscillations, that is, the amplitude of oscillation of X is much smaller than the amplitude of oscillation of the disturbance, and furthermore, we can see that these random jumps in the disturbance are relatively smoothened out. That is, our algorithm is able to attenuate the effect of the disturbance, and this is very important. Again, this algorithm can be tuned even better, and you can also improve it by introducing a disturbance observer. Links to the MATLAB code file and to this Simulink block diagram will be provided in the description below this video. Okay, let's start with the system modeling. As explained in our previous tutorial, whose link is given in the description below, the dynamics of this system can be described by the following equation of motion. The equation of motion is mass multiplying x double dot, where x double dot is the second time derivative of x, that is the acceleration of the mass, plus b multiplying x dot minus z dot. Over here, x dot is the first derivative of x with respect to time, and z dot is the first derivative of z with respect to time, and b is the damping constant. Then we have plus c multiplying x minus z. Over here, c is the spring constant, and this is equal to the force F, and this force F is the control force generated by the actuator. This equation actually follows from the Newton's second law. Let's divide this equation by 1 over m, and let's write it a little bit differently. 1 over m over here, then we have x double dot plus b over m x dot minus z dot plus c over m x minus z is equal to 1 over m multiplying the force F. Next, let's transform this equation. The idea for transformation is to move z dot and z to the right hand side since they originate from the disturbance z. That is, on the right hand side we would like to have the force, that is our control force, and the disturbance. Let's do that. From this equation it follows that x double dot plus b over m x dot plus C over M x is equal to, then on the right hand side we will have C over M multiplying Z plus B over M multiplying Z dot, and we will have plus 1 over M multiplying the force F. And this is our final equation of motion. Next, let's model the actuator. Here, for presentation clarity and brevity, I will neglect the dynamics of the actuator. That is, I will model my actuator, that is this block over here, as a simple gain. Consequently, we can write that force F is equal to gain of our actuator times the control input U. The actuator is actually the control input amplifier. That is, it will amplify U by multiplying it by G to create the force F. And that's it. And the final equation that we need to write is the equation of the PID controller. The equation of the PID controller is U is Kp, where Kp is the proportional gain multiplying the error, and we will define error later on, plus Ki, that is the integral gain, multiplying the integral from 0 to t, E of tau d tau, where this tau is a new variable necessary for integration and it's actually time, plus Kd, that is the derivative gain multiplying the first derivative of the error. The error is defined as, let's look at the block diagram, xd, where xd is actually the set point or the desired value for x, and minus the measured or the true value of x. To repeat, the PID controller is equal to proportional gain, Kp, multiplying the error, plus the integral gain, multiplying the integral of the error over time until the current time t, and plus the derivative gain, Kd, multiplying the first derivative of the error, where error is xd minus x. And that's it. These three equations, that is this equation, and this equation, need to be modeled in Simulink. Let's see how to do that. However, before we proceed with the Simulink modeling process, it's very important to perform one more transformation of this equation. Namely, let's write this equation describing the dynamics of the system like this. On the left side of the equation, we will leave x double dot. And on the right hand side of this equation, we will have minus b over m x dot minus c over m x plus c over m z plus b over m z dot plus 1 over m multiplying the force F. And let's call this right hand side as I. From this equation, it follows that x dot is actually an integral of the right hand side. That is the integral of I with respect to time. Then x is actually an integral of x dot over time. And these three equations will give us an idea for modeling the system in Simulink. Namely, first we will form the right hand side over here, then we will integrate this right hand side to obtain x dot, and then we will integrate once more x dot to obtain x. Okay, let's start with MATLAB modeling. The first step is to define the model parameters, and here you should keep in mind that we are defining these model parameters in a script. We are doing this because it's easier to define all the parameters in the script and later on to run this script. In that way, the Simulink workspace will be able to see all the variables and the model parameters defined in the MATLAB workspace. And this is a very good practice. Okay, first of all, let's define our plant. I'm assuming a mass of 300, damping constant B of 300, the spring constant of 10,000. Then over here I'm assuming that the force gain is 10,000. Then I define the PID control gains. The proportional gain is 10, the derivative gain is 0.2, and the integral gain is 0.5. Of course, you can play with these parameters as you wish. Next, I need to define a time series representing the disturbance input. To do that, we need to define a special data structure shown over here. First of all, I'm calling the data structure input data structure, and dot time will be an array holding time. The time will start from 0 with the step of 0.01 until 10. Then, however, keep in mind here that I have transpose. Then I'm defining the signal, that is the actual value of my time series for the time samples over here. Then I'm defining values, and over here I'm assuming that the signal is a sine function, and on top of that sine function I add a random noise. Then over here I'm closing the definition of the input data structure by specifying the dimensions of my input. I only have a single dimension. That is, I'm not having multiple disturbances acting in my system. And that's it. Next, evaluate this script. I usually do it like this. This is very important. Don't forget to do this and verify that all the variables and this data structure are in the MATLAB workspace. Okay, let's continue. Next, let's start the Simulink. Usually I start the Simulink by typing Simulink in the command window. Then, let's create a blank model by clicking over here. Over here, for the presentation clarity, I wrote the main equation defining the dynamics of the system. Let's start with the Simulink modeling. First of all, let's define the disturbance. That is, we need to define these two terms over here. How to do that? Well, double click over here and type in port. This block will actually import the input data structure from the MATLAB workspace. Enlarge it. Next, click on modeling and click over here. Next, click on data import export, click on input and type input data structure. This is the name of the variable that we previously defined. This variable, or better to say, this array or structure, stores the time series of the disturbance, and click OK. Now, let's double check that Simulink can actually access this time series. The best strategy is to try to plot it. Double click here and search for scope and connect this block with this block. Now click on simulation and click on run. And double click over here. Here it is. We can clearly see the input disturbance. Good. Close this, erase the scope, and let's continue. First of all, we need to multiply z, represented by this block, by c over m. In the Simulink terminology, we need to introduce the gain. Double click over here and search for gain. Enlarge this gain, double click on the gain, and we see that the gain should be c over m. And now we see that we have actually modeled z multiplying c over m. However, we need to model this part over here, b over m multiplying z dot. Let's create z dot. We can create the z dot by double clicking over here and searching for derivative. Then connect this part over here, and the output over here will be z dot. Let's add the gain. Here it is. Enlarge the gain, double click on the gain, and type B over M. Okay, now we have Z dot multiplying B over M. That is, we have this term and we have Z multiplying C over M. The next step is to sum these two terms. Let's click over here and search for sum. Here it is. Then we need to change the orientation of these ports of the sum. Double click here. Erase the vertical bar from the beginning and place it at the end. And connect. And let's name the lines. Double click over here and call this line Z. Move this block here, double click here and call this dot Z. Good. Let's do one more correction. Double click on the import block, then click on signal attributes, and over here put the port dimension to be 1 and click OK. Good. Let's continue. Next, we need to model this term, and we need to model this force term over here. Okay, we see over here that basically we need to sum three terms. We need to sum this term with the minus sign, this term with the minus sign, this term consisting of the two terms, and 1 over m multiplying the force. Actually, we need to sum the four terms, right? First, second, third, and fourth. This is very important. Okay, let's do that. Double click over here and search for the add block. We can either use the add block or we can use the summation block. To show you that you can do the same thing by using two different blocks, let's change and let's use the add block. Next, let's adjust the number of the ports of the add block. These two ports, the first one will accept this part over here. Then the second one will accept this part over here, and the last two that we need to add will accept this part and this part. So double click over here and add two minus signs corresponding to this term and this term. And let's connect. Connect this output of this summation to the second from the top port. Okay. This port will accept 1 over m multiplying the force. Now, the output actually of this add block is the right hand side over here. If we now integrate this right hand side, we will actually obtain x dot. So let's add an integrator. Here you should be careful. Search for the integrator and connect this add block to the integrator. The output of the integrator is actually x dot. Okay, now if we integrate the x dot once again, we will obtain x. Let's do that. Search again for an integrator. Add the integrator over here and connect this part. Okay, so this line is actually dot x and this line is x. Next, let's create these two terms. Let's start with this term over here. Double click here, search for gain, then click on the gain, click on format to rotate the gain, and connect the input of the gain to this line. This gain should obviously be minus b over m. Since we have minus over here, we simply need to specify here b over m. Here it is. Connect this output of this block to this part over here. Or actually I made an error over here. Don't connect it here. Connect it actually to the last port of the add block. You will see later on why this is important. Next, we need to model c over m multiplying x. Again, add the gain, rotate the gain, then connect this part to the gain, and let's expand this and type here x. X needs to be multiplied by c over m. Double click here and type c over m. Here it is. and connect this part to this part. Okay, now we have modeled this term, and these two terms. Good. To complete the model, we need three additional equations. The first equation is the force is equal to G multiplying U. Then the output of our PID controller U is equal to Kp multiplying the error plus Ki multiplying the integral of the error plus Kd multiplying the first derivative of the error, where the error is defined as xd minus x. Let's start with this modeling. Okay, the first step is to define the error. To define the error, we first need to define the set point xd. I will model the set point as a simple constant. Consequently, click here and search for a constant. Here it is. Then we need to model this minus sign. Double click here and search for sum. Then let's rearrange the ports and the signs of this sum. Double click here. Move this vertical bar at the end. And over here we should have minus plus. And let's see. Good. Connect this line over here. And let's call this constant by double clicking over here, set point. Okay. This port should be actually connected to the X. Let's do that. Here it is. The output of this summation block is actual error. Let's model our PID controller. Here's the PID controller. First, let's add the proportional gain. Double click over here and double click again and type Kp. Okay. Next, let's create the summation block or the add block. Click add. Then double click again. Increase one port. We need 3 ports over here since our PID has to sum 3 terms. Connect the top port to Kp and connect Kp to the error. Okay, now we have Kp multiplying the error. Let's create the integral gain. To create the integral gain, double click over here and search for an integrator. Here it is. Connect the integrator to the error, then double click, search for gain. The gain should be actually Ki. And connect the output of the integral term to this port over here. Next, we need the derivative action. So again here, search for derivative, connect this block to here, oops, be careful, to the error, double click over here, search for gain, and type here Kd. Here it is. Connect Kd to the summation block. Good. Now we have U. U has to be multiplied by G and then again should be divided by M. This can be actually modeled as a single gain, G over M. Consequently, type here and search for gain, and the gain should be G over M. Click on OK. And let's name the ports. This thing should be input U. Oops, be careful here since it should be down. Then over here we'll have error signal, you can call it simply E, and the output of this G over M should actually have the dimension of, you should be very careful here, since the dimension should not correspond exactly to the force, since we will have here G over M multiplying U. So this term over here will actually be equal to the output of this term. So you can simply connect this block to this add block over here. And that's it. Let me close this so you can see our model a little bit better. You can of course spend some time aligning the blocks, however I will not waste time doing this. The next step is to create a plot. To create a plot, we first need to introduce an MUX block. So search here for MUX. Then double-click on MUX and select 3 number as the number of inputs. We will need MUX since we want to plot 3 lines on a single graph. The first line will be set point. Consequently, connect the first port of MUX to the set point. Again, to show you over here, this set point should be connected here. Connect the second port of MUX to X. You see it over here. And the third port of MUX should be connected to the disturbance Z. Now you should be careful here when you're connecting, and here it is. Okay, good. Now the output of MUX should be connected to the scope. Double click over here and search for scope block. Here it is. Okay. Now we are ready actually to simulate our system. To simulate the system, click on Simulation and click on Run. And let's hope that everything will work as expected. Okay, open the scope block and here it is. Here is our simulation. Next, let's learn how to nicely format this graph. Expand this graph, then click over here. And this menu should appear. Over here, click on Time and click on Show Time Axis label. And you will see over here that time will show. Then again, click over here, click on Display, and over here on the Y label, type X, Z, set point. And click on OK. Good. Let's now see the legend. View, Legend. And here's the legend. Now, let's increase the width of the lines. Click over here on this arrow and you have this option called Style. You can also find Style on clicking View and clicking Style. And over here you can adjust the width of the line. Let's start with the first line, set point. Let's set the width, for example, to 2. Click on Apply and you can see it over here. Next, let's select X. Let's select 3, click on Apply. Okay, this is the response of the system. And let's improve Z. Here is Z, and for example, we can use 2. Click on Apply and click OK. And now you can see nicely all 3 lines. The yellow line is the desired position of X. The blue line is the response of the system, that is, this is the controlled X. And this red line represents the disturbance Z. We can see that the feedback control algorithm is able to significantly attenuate the effect of the disturbance of the system. This can be seen by comparing the amplitude of X compared to the amplitude of Z. And also we can observe that after some initial transient response that lasts for approximately 1 second, our X is able to relatively accurately track the desired set point. Next, let's change the value of the set point. Click over here and put, let's say, for example, -1. Click OK and click Run. Double click over here and let's see the output. And we can see again, even if we change the set point, the system performance is still relatively good. Okay, that would be all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot.